Let me introduce myself. My name is Stephanie Weirich. I'm also from the University of Pennsylvania. I also happen to be married to Steve, who was your presenter earlier. And if you see two small children running around, those are ours. Please ask them questions about type theory. Okay, so what am I going to be talking about? So I'm going to change gears a little bit. We're not going to be talking about Coq directly. I want to teach you how to implement Coq. Because sometimes I find that the best way to understand something is just to build it yourself. And so what we're going to do together is we're going to walk through a very, very simple implementation of a dependently typed programming language / proof assistant like Coq is, right? So, or like Agda is, or like Idris is. It's not going to be nearly as full-fledged out as any of those tools. It's not even going to be logically consistent. But it will give you an idea of what is the foundations of these logics that you're working with. We're going to be implementing something that's going to look sort of like the calculus of inductive constructions. Right? Now, so my lectures, partly I'm going to be just talking about how we specify a calculus like the calculus of inductive constructions. How do we specify it? How do we describe what type checks in this language? I'm also going to talk about how we implement that. How do we design a typing algorithm for this kind of language? And when I'm talking about implementation, we're actually going to look at a demo implementation. So who's programmed in Haskell before? Right? Okay. Don't be scared if you've never programmed in Haskell before. I pick Haskell as the demo language because it's sort of the closest to the mathematics. And honestly, most of the lectures I'm going to be giving is going to be in terms of mathematics, not in terms of Haskell. But I have put together some hands-on exercises, some of which is mathematics, some of which is programming in this language that we're going to be writing, and some of it is adding new stuff to the implementation. So if you're familiar with Haskell, you can play around, you can extend this implementation, you can add your own stuff to it. If you're not familiar with it, you can play around with the implementation itself and see what it can do. Now, let's talk about that implementation. How do you get access to it? So on GitHub, under my GitHub account, there is a Pi for All project. So you can see github.com/Weirich Pi for All. And I worked up this implementation last year for OPLSS. The master is for last year's version. We're going to work with the 2014 branch. So if you go to GitHub, and you want to start looking at this implementation, make sure you're looking at the 2014 branch. I've made some important changes between last year and this year, right? So that has all the code that we're going to be working with over the next 4 lectures. And I've even broke it up into several pieces. So today we're going to look at this much reduced version called version 1. And we're going to slowly build it up into larger versions. This one, SOLN, that has everything in it. Master is the version that generates all these different versions of it. The other important thing about this GitHub repository is that there are lecture notes that go with these lectures. So if you're following along and you want to know what I'm going to be talking about, in the repo this is the lecture notes for my lecture. So you can follow along here. If you see typos, you can give me patches for them. If you see parts that are unclear, help me build them out. I wrote these just for these lectures here. And so I appreciate any sort of feedback on it. The other thing is, so you'll see I have it all broken down into 4 lectures. I'm going to be really disappointed with you guys if I get through my first lecture. That means you're not asking enough questions. I really want you to ask questions. Make sure, don't get lost. Don't just let me talk to myself. Make sure I'm talking to you. Okay, so what are we doing? One more thing. So you saw the GitHub repo. You can access all of the source code. You can browse it on GitHub, or you can download it. If you're not very familiar with Git, I've also put up some tarballs. So if you want to get today's tarball, it's right here. There's the URL version1.tar.gz. You can just download it directly from my website. Okay. Right, just like that. Let's see. Okay, so we're going to be defining our own dependently typed programming language, right? So right now, this is our first program that we've written in it. It doesn't do anything because we haven't made the language yet. We have to figure out what language are we going to do? How are we going to implement it? Most of our discussion is going to be about the type checker for this language, because that's the part that I find the most interesting. In fact, I find it so interesting, I haven't really implemented any other parts of this language. Can't really run it, but you can type check everything. Okay, so what's in this language? So we're going to start with the smallest dependently typed core calculus that we can. And I just want to write the basic syntax up on the whiteboard over here, so we always have them. See here. So what's going to be in it? Right, so, and let me know if you can't read from this side. Right, so I'm going to use lowercase and uppercase letters both to represent syntax. You can't see it at all. Just not this color? Just not this thin marker? Let me see if I can find something better. Huh? What? Light on the whiteboard. Oh, you might be asking for too much. Lights. No, that didn't do anything. That doesn't do anything either. We now have lights on the whiteboard. Is this better? Can you read this? No. What? I can write on the other side. Then you guys, yeah. I can write it on both sides. That'll be fun. Yeah. Here's what we'll do. We're going to start. We don't need this for a little bit, so I'll do this, and then see if I can. I got this figured out. But I'm going to go. Right in the middle. Even if I can't figure out how to turn. Yeah. It's mostly white. Okay, can you see this? Yes. All right. Okay. The syntax of our language, right? What are we going to have in it? We're going to have variables. Okay? What else? What else should we put in a programming language? Just a simple dependently typed programming language. Types. What types? What are we going to put in this? Lambdas, yes. Lambdas. Lambda x dot a. Lambdas. What else? Application, yeah. All right. A applied to B. What else do we need? Types, right? And what kind of type do we need? We need an arrow type, right? A type for this guy, this lambda. It needs a type, right? And now, the thing about a dependently typed language is we're going to put all of our syntax together. So expressions and types They're all in the same syntactic class. And just so that you can keep it straight, what's what, I'm going to use the convention that when I'm talking about things and I intend it to be a program, I'm going to use lowercase letters. And when I'm talking about things and I intend it to be a type, I'm going to use uppercase letters, right? So if I wanted to add function types, I might write A arrow B, right? And I'm using capital A and capital B because I just mean for them to be types. Now, that's for a simply typed lambda calculus, but we want to implement a dependently typed lambda calculus. So instead of A arrow B, we're going to actually write a dependent function type, right? So instead of that, I'm going to write it like this to match the syntax in this implementation, right? We're going to name the argument x. It has type A, and that argument x is allowed to appear in the result type. Right? Now, if you've read mathematics about dependently typed programming languages, you might have seen this type written as pi x colon a dot b, or just now in Coq, you saw it written as for all x colon a comma b. So they're all different syntaxes for the same type. Right? These all mean the same thing. This is what I'm going to be using, and actually it matches Agda's notation. So next week when Ulf Norell starts talking to you about Agda, you'll see this a lot more. Okay, are we done? Do we need anything else? Huh? Universes. Okay, so we're going to have something that's called type. Right? And I'm only going to put one in. And if you remember, I said something at the very beginning. I said we're not going to be logically consistent. What did I mean by that? Type is in type. So what did I mean by that? Right? What does it mean logically consistent? That means that we're going to be writing something, we're going to be implementing something. We actually couldn't use it like Coq to prove theorems because it's going to allow us to prove false things, right? Now, what is a false proof, right? What does a proof of false look like? Yeah?
You produce an inhabitant of a type that can't have any inhabitant.
Yeah, we have, in general, and Coq has a notion of a type that we call false, and we call it false in Coq because there are no inhabitants, right? An inhabitant is a proof, and it's really good if there are things that are not provable. Because if everything is provable, yeah, it's really convenient if you want to prove things, but not so convenient if you want to make distinctions between what's true and what's false, right? Everything is going to be inhabited, and what's going to be that inhabitant? What is that proof of false going to look like? It's going to look like an infinite loop, right? It's going to be a program that runs forever. And so just like in Haskell, every type is inhabited in Haskell. Haskell is also inconsistent if you were to use it as a logic, right? We have the Curry-Howard isomorphism. All the Haskell types, you can push them through and turn them into propositions, but it doesn't make a very good logic because there's no false, there's no real false. There are no types that are uninhabited. That's going to be true here, right? Now, why am I doing it this way? Because I have to pick and choose. I only get 4 lectures. I don't get to do everything. So I have to pick and choose what complexities I'm going to show you. If you want to take this implementation and turn it into something that actually is consistent, you can. It's not too hard. I'm going to point out the shortcuts I'm taking, but I want to talk about other things, and everything that I teach you will be something you can directly carry over into something like Coq or Agda when you're trying to understand those systems, right? And so the first simplification is there's only going to be one type. Once you start learning about Coq, you'll find out that Coq has things like, it has set and it has prop, and then it has something called type, but really type is a whole collection of things called universes or sorts, starting from type 0 all the way up to any type level that you want, right? And that's what you would do. If you wanted to take our language here and make it consistent, you could break this universe up into various stratified hierarchy, just like Coq does. For simplicity, we're not going to do that today. Okay, but for simplicity, look at that. That's all we have. Yes?
So here, we're kind of mixed.
Yes, yeah.
So that's our type item?
Yes, we will. So, and Coq does this too, and Agda does this too. There's only, when you look at, Steve just now showed you the Coq program that you're generating with tactics, right? Like when he was doing one of the AND proofs, he showed you that it looked like a functional program. But that functional program, that syntax, it doesn't distinguish between types and terms syntactically. It uses the type system to figure out what's a type and what's a term, right? And we're going to do exactly the same thing here. Blue. Okay, that's our syntax. So now we need to talk about the type system, right? What does the type system look like? Now, who's ever worked with inference rules before, seen how you can specify something like the simply typed lambda calculus with inference rules, right? Okay, most people, but not everybody, right? And we're going to use the same notation, the same vocabulary, because this is a very powerful tool for specifying type systems, for trying to say, here's my programming language, here are the expressions that type check in it, and here are the types that they have, right? And what we do, we specify these things using a judgment, right? We write our judgment form that says there's some typing context that is going to tell us that the type of some program is this, right? So program A has type capital A. Or if you were doing Curry-Howard isomorphism, proposition capital A has proof lowercase a. Now this gamma, what's this gamma? This gamma is around to record our assumptions that we can use while we're type checking, right? When we have variables, we need to know what their types are. And gamma is going to keep track of what the types of variables are. Gamma is just going to be this ordered list of this variable has this type, this variable has that type. It could be empty if there are no free variables in our program. Hopefully, it has assumptions for all of the variables that are in the program. So we're going to use that when we're type checking, right? And in fact, let me write down our first rule. So this is the form. We're trying to conclude this relationship, this relation between gamma, the program, and its type. And we're going to derive that relationship using inference rules. So inference rules are going to start with axioms, and then there are rules from taking certain judgments and producing other judgments from them. So our first axiom is about assumptions, about variables, right? If we've made an assumption in gamma about the type of a variable, that's what its type is. So I'm going to write that just as the var rule, right? And typically we can name rules, inference rules and axioms just off to the side. That just helps us refer to them later, right? And that just says if we want to say that X has some type, then, well, somewhere in that list of assumptions about types, we must have assumed that X has that type, right? So this you can think of like a relationship between a context and some assumption about a variable of that type in that context. Okay? And then, so that's variables. The next step is for lambdas, right? If we want to show that a particular lambda expression has some type, when does a lambda expression, what type does a lambda expression have? It has an arrow type, a pi type, right? Even though there's no pi here, I will call it a pi type, right? So it has some pi type, but when does it have this pi type? What's the precondition of this inference rule for lambda abstractions? I'll call it ABS for lambda abstraction. What's the precondition? When does this lambda have this type? Yeah. Right? So if we put X, we assume that X has type A, and we put it in the context, and then we show the body of the lambda, right, has type B. Okay? Right, now, what can we do with this? Already we have two rules, and we can use these two rules to type check something. Right, so let's type check something. Okay, so over here, I'm going to use these two rules to construct a typing derivation. Right, so a typing derivation is just as a justification. It says, why does this program have this type? Now, what program do I want to construct a typing derivation for? Well, we're going to do the polymorphic identity function. So if you've written in Haskell, right, or OCaml, you can say something like this, right? I'll write it over here on this board because we're going to translate it to the syntax of pi for all in the middle board, right? So in Haskell, you can write something like this: idx equals x, right? This is a function. You give it an argument, it gives you results. What's its type in Haskell? What does Haskell write as its type? Right? If I wrote down a type signature in Haskell, what would I write down? A to A, right? I'd say this A to A. And it's polymorphic because this A, that's a type variable, could refer to any type. And if I wanted to, even in Haskell, I could turn on explicit quantification and I could say explicitly for all A. That's a dot. A arrow A. Okay, that's the type, right? For any type variable A, give me an argument of type A, you get a result of type A. How are we going to write that? We're going to write that in this language and type check it using these two rules, right? So we want to show in the empty context, I'll just write it like that what does it look like, right? In Haskell, you could write this program like this. You could also write it id equals lambda x arrow x. So that's a little bit closer to our syntax. But there's one other thing that we need to do when we're working in this language. One other thing that Haskell is doing for us that we're going to have to do by hand in pi for all, right? And that's abstract that type variable A. So over here, we're going to have to say for any type variable, and I'm not going to call it A because that's the meta variable I'm using for arbitrary expressions. I'll just call it, I'm going to call it Y. For any type variable, any argument of that type, I'm just going to return that result. And let's see here. There. And what type is this going to have? Well, Y should be a type, right? So here, notice in this arrow type, the first argument is a type variable. So I have to say it is a type variable. And the things that are type variables are things that have type. Right? So Y is a type, arrow. X has type Y, arrow. And then what's the result type? Y. Okay? Right? And now how do we prove that this function has this type? Right? Well, we use the abs rule, this rule right here. So the instance of the abs rule, so this is the general form, and now we construct a derivation by just filling in the blanks, figuring out what the variable is, what the body is, what capital A is, what capital B is. Right? So we can use the abs rule and say, well, this works if we take the context, add Y colon type to it, right? And then show that the body, which is another lambda, has the type, this part here, that's B, right, has that type. Right? And then why does this type check? Right? Why does this hold true? Why does this body in this context have that type? Well, we use the abs rule again. And we say Y is a type, X has type Y. That shows that X has type Y, that's B. And then finally, we're going to stop. Why does this work? Right? So here we use the abs rule. Here we use the abs rule. Here we're going to use the variable rule. We have a variable, right? And we have our context has an assumption about the type of the variable, but that's satisfied. right? And so we're done. We have a proof that this program has that type. Okay, any questions about this? Am I going too fast or too slow? Or okay? Okay. Everybody happy with this derivation? Yeah, looks good, right? Except we're missing one thing. There's one problem with it, yeah.
What if we had never introduced y?
Yeah.
We could still have,
Yeah.
our rule would have allowed us to add x subtract y to the context.
Yeah. Really, the question is, why does this make sense here, right? Right? And in fact, with these two rules that we have, we can verify programs that we like, type check, but there are also some programs that we don't like, and they do type check. And we need to figure out how to rule them out. So let me show you an example of a program that I don't like that is still going to type check, right? What about this one? Right now here, pretend I put numbers in. We'll eventually get to numbers, but pretend I've already done that. Right? That's the type I'm going to give for it. And then, so since I changed type, I'm going to do 3 and 3 here. Right? All of the rules still work. They still derive that this program has this type. But this type, it doesn't make sense. What does it mean for y to have type 3? 3 isn't a type. We don't want 3 to be a type. We don't want 3 to have any inhabitants. We don't want to use it in this way. So we need to somehow figure out how to rule this derivation out. And we're going to rule this derivation out by changing our abs rule, right? Right? The problem was this first step. When we put in the assumption y has type 3 into the context, that's a pretty lousy assumption to make, right? Because 3 isn't a type. So what we're going to do in the abs rule, we're going to make sure that when we add something to the context, when we add an assumption that A has this type to the context, that it's a real type, that it's something that we can be using as a type. So we're going to add a second premise that says that A is a type. Right? And hopefully we will not be able to derive that 3 is a type, because it's not. Okay, so what does that mean? Going back to our other example, what if I go back to type here? Now I have an additional premise, so I have to finish up this derivation. I have to fix it up with this. So what does that mean in this step that we have to set to prove? Right, over here I have to go extend the derivation. Wish I had written the line longer. Right, I have to show that what? That what's A in this first step? Right? It's type, right? So I have to show that type is a type.
The context is empty.
Oh, and the context is empty, correct. Right? So I have to show that type is a type, and then in this step I have to show that, what do I have to show in this step? I have to show A is y. I have to show that y colon type shows that y is a type. Right? So this one, we can just use the var rule again. That will work. What about this one? How are we going to show that type is a type? We don't have a way of doing that yet. So what we need is another typing rule. Right? We need to say type is a type. And so that's what we're going to add next. We just add another axiom. Right? When can type appear in programs? In any context, we can just say that type is a type. And this is the type and type axiom. And again, this is the axiom that is going to make our programming language inconsistent as a logic If we wanted to stratify it like Coq does, we would add indices to these universe levels. We would say type is actually in type I plus 1. But we're not going to do that. For simplicity, we're going to just collapse all these types together. So every type is in every other one. Okay. And with just this extra axiom, right, so the type in type axiom, we can finish out our derivation. Okay, so we're specifying this language. We've got typing rules for 1, 2, 3, 4 of the forms of this language. 1, 2, 3 of the forms. We have 2 left, right? We haven't had any rules that allow us to type check a program that had an application in it, and we don't have any rules that allow us to type check a program that has a PyType in it. So we need to define 2 more rules, right? So now what is an example of a program that we might want to write that has these forms in it, right? Like catching up with Pi for all, we want to be able to, in our language that we implement, we want to be able to say ID, right, X, what is it, Y is a type. Oh, is it? Oh, okay. How about that? Right, right, and we want to be able to say, we want our language to be able to say lambda y, lambda x, dot x has that type, right? And then we want to also be able to have some application, so some example, right? Maybe we want to be able to type check this example that's ID applied to itself, right? So in a Haskell, you can just say ID applied to ID, and it works out. That's not going to work out here because we have that type argument. We need to make it explicit. Ah. You're right. And this should probably be Y. Yeah. Right. So I'm trying to copy this example here. Our type checker is going to figure out this derivation for us, tell us whether it holds or not. Right? But I also want to do some examples with applications. Right? So in Haskell, we could just say ID applied to ID. But in this language, to apply ID, we have to apply it to the type of ID, right? So we have to take this guy here, that's ID's type, and give it as an argument, right? So what's going on here? ID has a first argument y, which is the type of the second argument. So this is the type of ID. So that's why I'm supplying it, right? And now this is something, oh, well, what type does this example have? What type should it have? Should we do this application? Same type as ID, right? Right? So we want this to work, right? But for this to work, right, we're going to have to type check. We have 2 applications, right? And in the application, we have this argument that is a PyType. We're also going to have to be able to type check that argument. So we need rules for those 2 things. Okay, so let's think about what should our rules for type checking applications look like. So I'm going to take away this example. Right here, move it down a little bit, and we want a rule for an application. When should A applied to B type check? What do we need to know about A? What do we need to know about B? Right? What type should A have? What should A be? A should be a function, right? Right? We're going to apply it to an argument, so it'd be a function. So if it's going to be a function, it better have some function type. So we'll say that gamma shows that A has some function type. Okay. What about B? What should be the type of, what do we need to know about B? We need to check that B is a good argument for this function. So we need to check that B's type, right, is capital A. It's the domain type of the function. And what is the result type of this application? B, right? So in simply typed lambda calculus, it's B. Here we have a problem, yeah. We have to substitute, right? And we have to substitute because this x is allowed to appear in B. And we don't want to have this type with this free variable x, right? X is there. It's standing for that argument. In an application, we know what that argument is. We know that argument is B. So we're going to fill that in. We're going to say capital B with lowercase b for x. We're going to do a substitution, right? So what that means, if you think about this example up here, when you apply ID just to its first argument, right? So what if I did this? EX0 equals ID just applied to its first argument, this type. What is the type of this? Right? What type does this have? Right? Well, it says take the type of ID, which is this up here. Right? Here is B, but go for all those y's and replace them with the actual argument. So it's actually a pretty big type. Right? It's the type of the identity function, arrow, type of the identity function. Right? And now to be totally precise, we have to give a name to that argument type, right? But we will, in our implementation, will allow our parser to be flexible that we could leave that name out if we wanted to.
You're giving the name because, from a formal perspective, like that might be bound somewhere in the result type?
Yeah, yeah. So this, well, the syntax of pi types, right? This syntax here requires a name, right? But in dependently typed programming languages, it's fairly common to use this abbreviation to say that if you see A arrow B without any name around, right, that means that's just standing for x colon A arrow B, except that B has no occurrences of x. Right? That's when it makes sense. So this is just a bit of syntactic sugar. In our Pi for All implementation, it's not too hard to support this syntactic sugar. But that's why we have to do that substitution, right? Because we could have those variables. And that's kind of the heart of dependently typed programming, is in this pi type, the fact that this B could depend on the argument. Okay, so that's application. But we still can't type check x0, our example 0 up there, right? Because if you look at the rule for application, you see that, okay, ID is a pi type. The argument has to have type, and so that argument in x0, ID applied to the type of the identity function, that type of the identity function has to have type. So we need a rule that type checks pi types, right, that we can use to show that the type of the identity function is a well-formed type, is a good type, right? And so this is our last rule that we're going to talk about today for this language, right? The one that says when we have a pi type, something x colon A arrow B, when do we know that is a good type? All right, so when should that be? When does this make sense as a type? What do we need to check about A and B? Yeah? A and B are valid types. So A is a type. And if we take the context and we put x colon A in it, if we assume that x has type A, B is a valid type, right? And so extending the context, that is allowing B to depend on x. Okay, that's it. I mean, so with this rule and that rule, we can go and construct a derivation for this example. I'm not going to do that. But we're going to write our type checker so that it will do this. And if you've downloaded version 1, you could type this in, and it should work. Fingers crossed. Okay. So before we talk a little bit more about implementation, I want to do a few more examples. Right? We're working with this very small language. Notice, right, we only have 5 things in it. Right? It seems like, what can you write in this programming language? Now, Steve mentioned in his just now that there was this thing called church encoding, where you can use the lambda calculus to encode other forms. Right? Who's ever seen or worked with a church encoding before? Right? Good. Who's done a churching encoding of AND, which Steve talked about? Right? I was going to do Booleans, but let's do AND, since that was the example before. So what we want to do is we want to encode the AND proposition, or the product type, they're the same thing, in this language, just using expressions in this language. Now, we'll just write it in this buffer here, so let's try to make sure we put it where we can see it. If I move this up, right, that should work. So, AND, right, what do we want AND to be? And how do we want to define AND? Right, we want AND to take 2 types and give us a type, right? Right, so and we're trying to represent the proposition P and Q, right? So and needs to have 2 arguments, and P and Q should themselves be types. Okay, so we want and to be lambda P, lambda Q, but then what we do with P and Q, that's the heart of the church encoding, right? We need some type that we can write just in what we have here. We haven't done inductive types yet, or data types, or anything like that. We'll get to that. But even before we do that, we want to be encode something that acts a lot like and PQ, so that we could use it to do things like show that and commutes, for example. That was a proof that you just looked at. Right? So somebody who's seen this before, right? What does a church encoding of and PQ look like? What type are we going to use? And the heart of the encoding is all in picking the right type, the right definition for this type. Any ideas? Yeah? What? P to C. Q to C. To C. That's almost correct. You did or instead of and. So how do I fix this up to make it and? Right. P to Q to C. Right. Right. Now, if it feels like you're pulling this out of nowhere, I feel like that too, right? I feel like you have to see a lot of examples of church encodings before they actually make sense. But what it comes down to it is you need to think about, how do we use and? What do we do with an and? Right? We use and by taking it apart, by providing some context, C, the 2 components of that, P and Q. So if we have a context that can use a P and Q, then that's how we want to use it. Okay, so that's the type and now we want conjunction. Okay, so what is the type of conjunction, right? We want conjunction to be something like this. Give me a P and a Q, and I'll give you and PQ, right? Except that we want it to work for all P and all Q. Right? So this is how we form ands, how we introduce these product types, or and. I call it product types because in the Curry-Howard isomorphism, and is isomorphic to a tuple, a pair of 2 things. Right? So, conjunction, yeah?
Okay. So I kind of getting into this, that we would be kind of blurring the distinction between
this is beyond my ability to intuit. Could you help me out with and there? What is actually going on? Why does that actually make sense? It looks like it's producing a value. What is it really?
So partly, and is a function on types,
Okay.
right? It's a function that takes two arguments and gives us another type. And so if you work with F omega, that's kind of the part, that's a calculus that allows you to write types, functions at the type level. In Haskell, I don't know if you use Haskell, there's something called type families, which allow you to also write functions on types. That way you can write something that says, here's something, it takes two arguments of the types and gives me another type.
There's also a direct correlation between algebraic data types and church encoding. Like your definition for and, if you think of and as a data type, it would be a data type of a single constructor taking two arguments. So this and function is just returning the and constructor, which is a function that takes two arguments and returns you a constructor type. Likewise, you can go the other direction. You can take any simple algebraic data type, and you can convert it into church encoding by using a function argument for every constructor and an argument within each function argument function type for the different parameters for that data constructor. If that makes sense. I would meditate on that.
Yeah, look at a lot of the examples and then go back to the comment. It's exactly right. You can generalize this to arbitrary constructors.
Just one clarification. You said the constructor type is that second thing, P or Q or C?
The type of the and, the constructor type is actually the whole thing, right? Because it generalizes over C. So C belongs to. Yeah.
And so just so I'm clear, these arrow types are automatically everything that follows is, and so this is also a thing, right?
Yeah. Okay. So if you've seen something called a dependent pair, like a sigma type, that is not this.
Okay.
Right. And the reason it's not this is because Q is not allowed to depend on P.
Okay.
And we can talk about sigma types. Yeah.
We might want to make C a dependent type.
We might want to, yes, we might want to make C a dependent type. We will also talk about that later. Right. Yes. Right. We might want to let C know what P, that's eliminating a pair, and exactly what pair it's eliminating. But we'll again talk about that when we get to more data. Okay, but let's just finish out this definition. Right? What is conjunction? What's the definition? Right? We want to introduce something that has an and PQ type. Right? And just looking at that type, we know that we need P, we need Q, we need X of type P, and we need Y of type Q. We need all these things, right? We have the type of conjunction that says we need 4 arguments. How do we take these 4 arguments and give us something that is and PQ? And PQ, right, that's this type. Okay, so what do we need there? Yeah? Okay, yeah, so now we're working on this part here for and PQ. So we need a C, and then we need an F. That's this guy, an F. And now, what do we do with F? F, X, Y. And then we're done, right? Is that type check? That should be our first question over, does this make sense? Does it even type check, right? So I argued why we needed P, Q, X, Y. X has type P, Q has type, or Y has type Q. C is the type, it's part of the definition of and. F takes a P and a Q and gives us a C. We need a C in the end, so all we have to do is give the right arguments to F. We need a P and a Q, but that's what X and Y are. Right, so it does type check. Right, what does it do? Right, conjunction is just remembering 2 things for later. Right, so when we apply conjunction to X and Y, that's the 2 things we're remembering. Right, and what is later? Well, when we pass in F, that's what we want to do with those two things, right? And so F gets access to them. Okay? Yeah?
C represents in the AND type.
Why do we have C?
Why do we have C? Well, when we do something, what F is, right? What we do with these two things, we want to do arbitrary things. We want to do anything we like with X and Y.
So
and
C
we want
is,
to make it polymorphic, right? So C is the result type.
so F is the effectively the projection function back out of the AND.
Yeah, it's F is like the pattern match, right? Okay, so let's, yeah, the eliminator. Let's do an example of conjunction. Do you want to do one, right, with this encoding, right? We have a way of taking, of defining an AND type, of creating a conjunction. Now, proj 1, it should look like this, right? Give me two types, P and Q. Give me AND PQ, and then I'm going to take that AND, eliminate it, split it apart, and just give the first component. Right? So we should be able to define proj 1 just using these definitions. Right? So what is that? So again, we need lambda P, lambda Q, and then we need our AND, right? I'll call that A. It has type AND PQ. Now, if we have A, it has type AND PQ. How do we use it to get a P? Right? Well, we have to look at the definition of what AND PQ is, right? So A actually has this type right here. Yeah, so we need to apply A to what? To P, right? That's P is going in for C because the eventual result we want is something of type P, right? And then we need a helper function, something that has type P arrow Q, and then we just put in P for C, so it's P arrow Q arrow P.
So lambda x, lambda y, x.
Yeah, lambda x, lambda y, x, right? So A is this, and it's saved two things away, and we're passing in for F, we're passing in this function that says those two things, x and y, that you saved away, give me the first one. Right? And so if we wanted to do proj 2, right, it would look a lot like proj 1, except for one important difference. Right? So proj 2, right, this time we're going to produce a Q, and we're going to pass Q as in for C. And then here, when we say give me the two things, give me the second thing. Right? So now we've defined our two eliminators for our conjunction. Right? Does this make sense? Do you want to do one more example? Right? So should we do this? And commutes. How can we do this, right? We want to take AND PQ and produce AND QP. How can we do that? Lambda P, lambda Q, here's our AND. What do we do with this AND to swap its components around? Oh. Okay. You want to do conjunction? You want to project out 1 from A, project out 2 from A, and then use conjunction to put them back together. Okay. So the top level thing is conjunction. Right? We'll put two things back together. What are the two arguments to conjunction? P, Q, and then we want to project out the P. Huh? Oh, QP, we're swapping them around. So QP, and then we're going to project out the second component of A, but we need to do this is PQA, and project 1 PQA. Yeah. So in Coq, you use tactics to generate things like this, right? We wrote out this lambda calculus dependently type CIC term, or just CC, just this. We wrote it all out by hand, and you notice we had to, it was kind of tricky, right? Coq and AGDA are really good at trying to figure out arguments like Q and P here, the dependent, if there's an argument that who is actually dependent, that means that appears in the type of a later argument, that's a really good opportunity for type inference to figure it out. AGDA and Coq can do that. We're not going to do that today. That's something beyond the scope of what we're going to be talking about, right? And Coq also goes the extra step of having a meta-programming language, the tactics language, to help you create these expressions like this. In AGDA, you're actually going to write them down explicitly, but having type inference around in AGDA also really helps. And Ulf will also show you that the Emacs mode for AGDA also is going to help you interactively develop things like this. We're really masochistic here, doing it all by hand. But we know we really understand it. Yeah?
And commutes would just be to take the A and then just pass in and QP and conjunction QP.
Okay, so this is not the only proof of AND commutes, and you're saying we could have taken the A, right?
And then pass in and
what?
QP.
And QP, right?
And
We want to take A, eliminate it, produce an AND with the two arguments split, and then lambda X, lambda Y, conjunction QP Y X, something like that, right? Yeah, that should also work.
You should compare those two proof terms, the two different proof tactics of the conjunction that we talked about last time. That's exactly the difference between them.
Okay. So that is an example of some code that we can do in this very simple programming language, except that we have to implement it. We haven't talked about implementing it, right? What we've done so far, right, is defined these typing rules here, right? So we have these rules, and let me just get some more white space here. Right, so we have these rules, and it would be really nice if we could view these rules as a typing algorithm to tell us if we're given a typing context and we're given in a program, can we figure out whether that program type checks and figure out what the type of that program is? These typing rules are really close to that, but they don't quite work. Right? We can't just read these typing rules as some algorithm that we can go and then implement in Haskell. Right? So the real question I'm asking is, how do we take this specification of our type system, right? We specified this judgment, right? But what it is it's not syntax directed. We can't use the syntax of the program to figure out what the typing algorithm is. Somewhere there's some guess that happens that we're smart, we can do that guess when we're creating derivations. But if we're writing a type checker, our type checker is not going to be that smart. Some part that's not straightforward. So there's one rule here where we're making a guess, right? If I was just saying, here's a program, I'm going to start type checking it. Any ideas what rule is causing our problem, is causing difficulty? Right? Someplace where there's some information that we don't really know from the term itself. Application. So let's see if we can read application as a type inference algorithm. Right? So in application, we might say we have some context, we have a program that looks like A applied to B. What would our algorithm do? It would look at A, call itself recursively, says, okay, this application is going to type check if A type checks. What is the type of A? I'm going to get out its type. Let's make sure that its type is some pi type. Pull out the type A from that result. Type check B, call the type checker recursively on this argument, find out its type, compare that type to A, and then we're going to use, then we still have B over here, and substitution, we can substitute and generate the type. So application actually is syntax directed. It's specifying an algorithm for inferring the type of this term. So application is fine. There's still some details that the rule glosses over that our type checker doesn't, like figuring out that A actually has a pi type once we get its type, pulling out the domain type and comparing it to the type that we get from B, right? We have to do that explicitly in the algorithm, but it's still defined by the syntax of the term. There's no guessing that we had to do. Right? Well, let's go through some of the other rules. So variables, if we're given the context in a variable, we can just look up in that context to see. Right? So the variable rule is also syntax directed. What about the abstraction rule? Right? We're given the context in a lambda expression, and we need to extend the context and check the body. But where does this A come from? Right? We don't know. We just guessed it. Right? We need to extend the context to call our type checker recursively. We want to type check the body of the function, but we don't know what type we want to use as the argument type. Right? We didn't write it down in our syntax. Right? So this rule, this is the rule that's the problem. This is the rule that's not syntax directed. This is a rule where our algorithm, when we were trying to implement our algorithm, we would get stuck. Right? We wouldn't know what type to use, because if we picked the wrong type, then A would just not type check, but maybe there would be some type that it would. And how would we know which type is the right one? Now, programming languages like Haskell use unification to figure that out because they're working in a restricted language, and they can. We're not going to do that. Right? What we're going to do is we're going to revise our rules so that they are syntax directed. Right? And so what we're going to do is we're going to define a new type system that's a lot like this type system, except that every rule in that type system is syntax directed. Right? And once we've defined that new type system, that's the type system that we're going to implement. So what does that new type system look like? The problem is that we can't always infer the type of a term. Sometimes we just don't have enough information to figure out what the type of some program should be. So we're going to take this judgment right here, right? These rules define a judgment that has that form, and we're going to take that judgment and divide it up into two pieces. One piece that works when we can infer the type of the term, and one piece that requires extra information. A piece that requires the type can check the type. If we know already what type we're looking for, then we can just verify that that term has that type. Right? So we're going to replace this one judgment with two judgments, and it's going to look awfully similar. But these two judgments are going to work together to specify an algorithm for that. Right? So we have checking mode. If given a context and a term, figure out that that program has that type. And so I have the arrow because we're looking at the program and producing its type from it. And then we also have a version called checking mode where we're provided a type as well as the program, and all we want to do is verify that indeed this program has that type. And checking mode, the checking part of the judgment, is going to fix the abstraction case. Right? Because if you think about it in checking mode, right, if we rewrite this term that rule, lambda x dot a, if we get to know what type we are trying to check, then we have that a. That was the problem. We didn't know what the type of the argument was. But if somebody gave us the whole type that we were trying to check it with, then that's the missing piece. That's the information we need to stick into the context and keep that the body has a particular type. Okay? So the lambda rule, the abstraction rule, is going to look like this. What about the other rules? All of the other rules, right, we can turn into inference rules, right? And all of these other rules, we can go over here. Let me see. I'm going to write the inference rules on this side. Right, so for variable, we can infer the type of a variable by looking it up in the context. For type, if somebody says, what is the type of type? We know it's type. For pi, for function types, if we have a pi type, what is its type? We know it has to be a pi type, right? We can just tell you that it's going to be a type. When does it have this type? Right? When does this pi type have type, right? Well, when the argument, right, we can check, we know what type we want to check A to be, right? So we can check that A is a type, and we can check that B is a type. Okay, and then one last rule. If I write it here, can you see over there on that side? We can, if we have an application, right, we can infer that it has type capital B with B for x. And when can we do that? Well, if we look at the argument and infer that it has some pi type, and then when we go, or we look at the function a, infer that it has some pi type, that tells us we want this guy, B, to have type A to match. So B, we can check with capital A. So as long as B has that type, then this is the type of the whole application. All right, now these two judgments, right, I wrote them as two separate judgments, but you kind of have to think of them as one system because you see how they interact with each other. That this, for example, this rule, it's a checking rule, but one of its, it's an inference rule, but one of its premises is a checking rule. All right, and so this is how we're going to implement our type checker, to be able to implement our type checker so that all of this code up here can be verified by our algorithm. So think about, I wrote this code like this for a reason, right? The name of the thing we're defining, its type, and then its definition, right? And why did I do that? Well, look at a lot of these examples, like proj2. We know its type is going to be that type, right? And the definition of proj2, it's a bunch of lambdas. It starts off with a bunch of lambdas. But that's okay. We know what type we want proj2 to have, and so we can start checking that lambda, right? We can start checking all of those bodies, right? So we can check that, check this lambda against the whole type, check that lambda against the subtype, check that lambda against that type. And then what happens when we get to this point here, right? This rule says you need to keep checking, right? But now maybe we're a little bit stuck, right? Because that rule says you need to keep checking against, in this case, Q, but we have an application. And all we have over here is a rule for inferring the type of an application. but we still want this to type check, right? And the fact that we can infer a type for a term, can we still check that that term has that type? Could our algorithm kind of go between the two modes?
Infer the type and then see if it's equal to the type that you want to check it out?
Yeah. So we need one more rule, right? I'll write it here because I have the most space, right? It says that if we infer a type of a term, right, and we wanted to be able to check, and we were checking that a term had that type, right, and so we infer some type, as long as those two types are equal to each other, then that should be fine, right? We should be able to check a type by first inferring it and making sure that the type that we infer for it is the type that we were expecting. Right? And that's the missing piece. That's what we need to do there. When we get to that application, we switch from checking mode, checking that that has type Q, to inferring its type. And then we do all the applications in inference mode.
So these arrows going left and right are different types of judgments, right?
Yeah.
Type checking and inference.
Yes.
So if you had a judgment that lets you go from the other way, from left to right, then you collapse the distinction between the two.
Yeah. Okay. So let's talk about the. So he's saying, okay. So here we were going from inference to checking. What about a rule that went from checking to inference? Right. So, what if we had a rule that looked like this? It said, if we could check the term has type A, then we could infer it has type B as long as A and B make sense. Right. Does this rule, can we implement this rule with our algorithm? If we're writing an algorithm where, imagine we're writing an algorithm, our algorithm says, I'm giving you the context, the term, and its type. Make sure that that term has that type. Right? Oh, no, sorry, backwards. I'm giving you a context and a term. You tell me what its type is. Right? And so you want to do that by switching over and say, okay, I want to call the checking function, but where did this argument come from? Right? It comes out of nowhere. Right? So inference only gets the term, it doesn't get the type. Right? So we don't have this A. Right? This rule here is not syntax directed. Right? We're missing a piece, and so this rule doesn't fit in an algorithmic presentation of our type system. Right? And like you observe, this is kind of erasing the distinction between typing and checking. Right? And what that means, though, what you are also close to observing, is that there are programs that type check with this judgment that don't type check with these. Right? We're actually missing a little bit because we've dropped out this rule. Right? So. Yeah.
So I had a question.
Yeah, sure.
So in this rule where you have the A equals B, isn't that where you would normally do the unification?
Yeah.
During that check?
Yeah, there might be some. So I don't really want to get into how things like Haskell uses unification to figure out these types, but yes.
Okay.
Right. That's part of the story. It's not quite the story.
So what is the difference here where we're not using unification?
So here, this is just syntactic equality, right? So actually, I could have written a rule without B, right? I could have written the rule like this, but I wrote it with the B because if you think about what the algorithm has to do, it actually has to do like an alpha quality check right here and make sure that these two things are equal types. So I'm making that explicit. Question? Yeah.
Do we generally have to do some data reduction as well?
Yes. We're going to get to that in the next lecture, right? You're right ahead of track, ahead of schedule. There is a fundamental limitation of what I'm showing here because our equality right here is really weak. And we're going to talk about what happens when we make it stronger and what things do type check and don't type check with different definitions here. that work together that are syntax directed. But then I said to you, we didn't quite get everything. There are things that we can write derivations showing that they type check with this judgment, but we can't use these two guys to show that they type check. Right, and so I'm asking you to think really hard now and try to see if you can figure out what we're missing. Somewhere, there's some program that is not going to type check. So what would an example of that program be? Yeah. Yeah, so look at this application rule, right? It says that in an application you have to infer that the argument has a pi type, but our rule for lambda over here only lets us check lambdas if we already know that that's a pi type. So if we have an application where the first argument isn't lambda and the second argument is something else, right? So if we had written down in here, example 1 equals lambda x dot x applied to lambda y dot y, right? That is not going to type check. Right? We're not going to be able to type check that with our system, right? Because our rules will say that in inference mode, right, you can't have a lambda, but the first part of an application has to be checked in inference mode. Is this really bad that we can't type check this program? What if we wanted to type check this program? What could we do? You'd have to spell ID out. Yeah. I mean, we could just write down ID, but
You require the user to specify the type of the lambda.
yeah. So we could extend the syntax of our language and put a type right here, right? I don't know what type we're going to do in this example, but we could actually write down the type and have a version of our algorithm that just there for when we have these explicit applications like this that allows us to go to lambda expressions but work when we're in inference mode because we wrote down what that A was, right? And since we wrote down in the syntax what the A was, we don't have to guess, and so we can write an inference mode version. More generally, we could add an annotation form to our syntax. We could go over to the syntax of the language and say, I'm going to extend it with a new form that says A has this type, right? And then over here, we can make this rule syntax directed for that annotation form. Right? Maybe I don't need to have A's and B's there. But if you have an annotation, that allows you to have the bridge from one mode to the other mode, from inference mode to checking mode, right? I wrote down, we're in inference mode, but we can't infer this type. We can only do it in checking mode, but I wrote down what type you need to use when you're in checking mode, and that's the type you're going to infer for it, right? So we could add an annotation form, or the final thing we could do is not care, right? Because look at this term. How many of you write programs that look like that? With explicit lambdas applied to arguments. Huh? Oh, a let, though, that names it, right? I'm saying if you name it, you know what its type is because it's a variable in the context, and that works. We can infer the types of variables. I mean, how many of you write programs where you write lambda applied to arguments? Yeah? It's fun, yeah. Yeah, and Coq just generated one from the tactics. Steve showed you one. But you don't really do it so much, right? Usually, you do that beta reduction. Usually, if you know of the lambda and you know its arguments, you actually write the program after the substitution has happened, right? Right? And what it means is that when we've written our typing rules in this form, we actually can't type check any programs that have beta reductions in them, right? because it's the beta reduction. Program with the beta reduction. That's exactly the program that we can't type check. And I'm not so much bothered that we can't write programs with beta reduction. That would be simplified by just doing a beta reduction. Because I could have written it, I could have done that beta reduction myself. That version would work. That would type check. And then we would be done. Right? And as you see, so we're starting with just this very simple language. But as we add more things to it, I want you to notice something. Right? So the introduction form for lambda, right, that's in checking mode. The elimination form over here is in inference mode. The fact that the introduction and elimination form are in different modes, that's what prevents us from checking something that has a reduction in it, right? When we start doing other forms, the pattern is going to hold. The introduction form is often going to be in checking mode. The elimination form is often going to be in inference mode. And so when we add other things to this language, there will be other sorts of reductions that we won't be able to capture. Now, we still have things like annotation, if we really wanted to put those in, right? So annotation is general. It'll work for anything, right? But what it really means is in the programs that we really want to write, like all of these that we wrote up here, right? We don't actually need to have any internal type annotations. Just putting the type at the top will generally be enough. Okay, so it's just about lunchtime. I think I'm going to stop here. We haven't really got to the Haskell code yet, but I'll pick up in my next lecture how we can take these two different judgments and put them to use in some Haskell code and implement them so that we can get something that will actually verify these examples that we've developed here.